All right, so welcome back to the structural engineering section of the Civil FE exam review. Today we're going to be continuing our review with column analysis. And so I have a few practice problems for you all today. And if you've missed any of the previous videos on structural engineering or just in general, such as, your mathematics, ethics, engineering, economics, or any of these topics, make sure you go back and check those out. You don't want to be skipping sections, subsections. You want to make sure that you have knowledge of all of the material that's going to be on your exam. All right, so let's go ahead and dive in. All right, so number one says, determine the critical, and I had this loaded wrong, but determine the critical buckling load for a slender steel column that is pinned with a unbraced length of 4 meters and a modulus of elasticity of 200 gigapascals. Moment of inertia is 0.00002 meters to the fourth. It's a lot of zeros. All right, so what information are we given? Well, we're given the unbraced length. We are given the modulus of elasticity. We're given the moment of inertia. It says it's pinned. Don't know if this is important, but it's pinned. And it's a steel column. Steel column. Okay. So it says find the determine the critical buckling load. Okay, so we're trying to find the critical buckling load. All right. So I'm going to say critical. I'm going to search critical buckling. I'm going to search critical buckling. Okay. And so when I do that, come to this section. And so this is the critical buckling stress. But the critical load for a long column subject to buckling is, you would use this formula. Okay, so based on this formula, we got PCR, which is the critical buckling load, right? What's pi? Well, we know what pi is. What's E? E would stand for modulus of elasticity. I is moment of inertia. And then K, what's K? It's the effective length factor to account for end supports. And so the theoretical effective length factors for columns include, okay, you got a pinned, fixed, pinned, and fixed free. Which one are we using? Well, we got pinned. So K equals 1, right? All right, what's this little L symbol? Okay, L is the unbraced column length. Well, our unbraced column length is 4, right? So it looks like we have all the information that we need. What I'll do is I'll just write this out again. So we'll say the formula needed is PCR is equal to pi squared EI over KL and then squared. Okay, so E is equal to 200 GPa typically you want to get all units in meters or newtons. So I'm going to get all my units in meters and newtons, and then at the end, when I get my answer, then I'll just convert it to whatever the unit is. So it'd be in kilonewtons. So I need to get this in meters and newtons. So 200 gigapascals is the same as saying I would multiply this by 1 times 10 to the 9th to the 9 power. And so 1 gigapascal equals 1 pascal. And then I know, and how did I know that a gigapascal is times 10 to the 9? Well, I would go to my unit conversions if you didn't know this, right? If you can remember, then you're good, right? Okay, giga. Can't even see this. All right, giga down here is G, and it's times 10 to the 9. Its multiple is 10 to the 9th. All right. Now, how many newtons are in a pascal? Let's try to go back to where I was. All right, how many newtons are in a pascal? 1 pascal is equal to 1. You guys aren't seeing this. All right, let's try. All right. 1 pascal is equal to 1 Newton over meter squared. So 1 pascal is equal to 1 Newton over meters squared. So just something to keep in mind. So typically I will just leave it in pascals, but at the same time, if I ever need to flip it to newtons over meters squared, I can. So just something to think about. But typically you want all your units in newtons or meters. Okay, so now we just we got I is equal to 0.1234. Is that 4 zeros? Yeah. 0.0002 meters to the 4th. All right. K is equal to 1. Where did I get K is equal to 1? Well, it's pinned. All right. We had critical buckling. Going back to our formula so you can see. All right, so K is equal to 1 for pinned. All right, L is equal to the unbraced length, which is 4 meters. That's what we're given, right? That's why I'm getting you to write out your givens, because from this information, you'll know what variables you're looking for. So this is all equal to, let's plug and chug, pi squared times, let's say 200 times 10 to the 9th newtons over meter squared. Okay, times 0.00002 meters to the 4th. Okay, and then all over K, which is just 1 times, what's my L? 4 squared. And I'm going to write out the unit so you're not confused. 4 meters square. All of this is in parentheses square. All right. So I get my answer to be 2,467 kilonewtons. Or B. So that is the critical load. So what they're saying is we have this column, right? It's on the ground, and we have a force coming down. P critical. So when will this thing start to buckle? What I mean by buckling is when will this thing start to kind of do like another one where I'm showing that it's buckling. This is a drastic kind of, whoa, not that much, but it's basically where it's getting wobbly, right? So you've put that force down, and it's causing it to basically curve and bend, right? Or buckle. If your legs buckle, they kind of give out, right? So it's the same thing with the column. All right, let's look at number 2. All right, what is Euler's buckling formula used for in structural engineering? All right, this is a conceptual question, right? All right, so what information are we given? We're using Euler's buckling formula. Okay. And we are trying to find what this formula is used for in structural engineering, right? So we're in the area. If you haven't found this, you can search in the handbook critical buckling, or Euler's. You can even search Euler's, but we're already in the section that we need to be in. So Euler's formula, and so is it for determining critical axial load for load column subject to buckling? So is it to determine shear forces in beams? No, this has nothing to do with shear force. Now the variables are shear force. The loading isn't shear force, so no. Is it analyzing bending moments in columns? No. Nothing to do with moment in this equation. Bending moments, all that stuff. Predicting torsional stress in shafts? No. Or assessing stability of slender columns under axial loads? Yes. It's critical axial load being placed on the column, and so you trying to see how stable your column is going to be. So a little bit of prior knowledge, but you are in the column section, so that does help. But just knowing what you're doing, right? Knowing that anytime you're using Euler's formula, which they are going to test you on, there's some type of axial load that is being applied to your, just call it 8 newtons, to your column. And at a certain point, trying to find the critical, point that, or the critical force before it begins to buckle, right? And bend. So our answer is going to be D. And let's look at number 3. This one says, find the slenderness ratio for a reinforced concrete column with a length of 5 meters and a cross-sectional area of 4 meters squared and a moment of inertia of 2.1 meters to the fourth. So a bunch of information. Let's just start by figuring out what we're given. So we're given the length of the column. We're also given that it's a concrete column. We're given the length. She's a different color. She's red. And we're given the area. Okay. So we know area, know concrete is a concrete column, and we know the length of this column. Oh, we know moment of inertia too. Okay. Cool. All right, what are we trying to find? It says find the slenderness ratio. Okay. So how do we get slenderness ratio? I don't know. Maybe you all know, but I don't know. So I'm gonna slenderness. Let's look up slenderness. All right. So the effective slenderness ratio for the column is KL divided by R. Okay. Is that what we KL over R? Effective slenderness ratio. Slenderness ratio. SR. So what is SR? SR, the slenderness ratio of a column, SR is equal to L over R, where L is the length of the column. Okay, we have the length of the column. Check. So length of the column, and R is the radius of gyration. All right, the radius of gyration. So do we have R? So the radius of gyration of a column cross section is R is equal to the square root of I over A, where I is the moment of inertia. We have that. And A is the area. A is the cross-sectional area of the column. Cross-sectional area of column. Okay. So we have L and we have R, and that'll give us SR. So let's solve. So I know that the formula I need for the slenderness ratio of a column is SR is equal to L over R, where R is equal to this, square root of I over A. All right. And then L is equal to the length of the column, which is 5 meters. All right, let's solve for R. R is equal to the square root of 2.1 meters to the fourth over 4 meters squared, which is equal to 0.7245 meters. Okay, so now we know that our radius of gyration, that's what this says, right? R, radius of gyration of the column cross section is going to be 0.7245 meters. All right, so we have R, we have L, We have L, we have R, and now we just need the slenderness ratio, which is what this question is asking us to find. So SR is equal to L, which is 5 meters, divided by 0.7245 meters. Now, once these units cancel, that's why it gives us a ratio. SR is equal to, when I plug that in, I get 6.9, no meters, it's not 6.9. All right. So that is my answer. Answer is A. All right, so that concludes the column analysis section for structural engineering. We are going to be looking at structural determinacy and stability analysis of beams, trusses, and frames in our next video. So I will see you in the next one.